I mean, obviously, this is a workshop where people are most interested in protein structure, function, and dynamics. But since I'm the methods guy here, I decided to just double down on the methods and just talk about a few things, some more established and some more recent methods on the front of machine learning for physical chemistry and biophysical systems that might be interesting to you. And so generally, as Enrica said, we're called AI for Science as a group. And the idea here is that, of course, there's a lot of AI and machine learning applications going on in pretty much all fields in the last couple of years and in the years to come, I assume. And so when you are developing machine learning systems, and here are a few famous ones like robotics and control and reinforcement learning for playing games, then essentially you have to decide to fundamental, you have to address the fundamental questions. So one is, how do you formulate your machine learning problem in terms of an optimization problem? Because essentially all machine learning problems are formulated as optimization problems. You're optimizing something. So what is that something? And the second question is, what is the learning structure that you're optimizing? So what's the structure that holds your variables or parameters that you're optimizing? And that could be a neural network, a kernel machine, or something else. Okay, and in the sciences, and especially in the fundamental sciences, such as physics and chemistry, and biophysics, we have a lot of fundamental knowledge that we can leverage in order to answer these questions. So in physics, very often we have basic principles such as variational principles or some self-consistency relation that we want to use in order to define the learning problem, the optimization problem. And also in order to get physically meaningful results and models that we can meaningfully simulate and then do and interrogate in a meaningful way so that we can extract expectation values or observables that make sense. We often have certain requirements to the model as well. So for example, certain symmetries like an energy of a molecule, an implicit solvent or vacuum should be invariant to translation and rotation, etc. And so we better build that into our machine learning models, these structures, in order to get meaningful results and in order to be able to do the operations that we want to be able to do later. For example, put this into an MD simulation engine and run it and hope that the energy doesn't explode or do random things. Okay, and so here I will talk about a couple of the topics that we are working on. So particularly about kinetics, that's kind of our bread and butter topic, Markov state models, and then Benoit has just touched on that. So I'll talk a little bit about that. Then I'll talk about the sampling problem and new methods on that side, and finally the coarse-graining problem, coarse-graining MD, and all of that with machine learning. So let's begin. So here's a simple system that we have worked on and many others have worked on probably before the time that I was born. Barnase bar-star, a small protein-protein system. Bar-star is the natural inhibitor of barnase, and these form a very tight binding complex. So here is an energy function, and basically the idea is that there's some unbound state that has a higher energy than the bound state, and so it takes a very long time to escape the bound state and dissociate the two proteins. And so if we define a thermodynamic ensemble together with this energy, we also define a probability density, and this is really what we want to sample in MD simulations or in Monte Carlo methods. Okay, problem of course is the sampling problem. So it could take us a week on a GPU to do 1 microsecond simulation. Now the typical time to bind in this particular setup here, in this solvent box, is about 50 microseconds. So that would be 1 GPU year. Now it's a bit less with the newest GPUs, but so this is order of magnitude. And it would take about 1 hour of real-time real-time that corresponds to 1 million GPU years to dissociate the two proteins spontaneously, and that's obviously not a very sustainable approach. Okay, so Markov state models, the idea of Markov state model is kind of to divide and conquer this process, to divide the state space into substates, different conformations or metastable states, or also non-metastable states, but the main idea is to be able to distinguish the metastable states, so the long-lived states in the energy landscape, and to use the fact that if we do this well, we can reconstruct the dynamics, or at least the long time part of the dynamics, or the kinetics, by learning the transition probabilities or rates between these metastable states. And then we can use short simulations that start in different metastable states, and we just essentially get the statistics of how often they transition to other states, rather than having to have one super long simulation that visits all the states according to their equilibrium distribution. Okay, and this has been developed by many years by several groups, my group included. And so here are a few basic principles I need to introduce before being able to talk about machine learning for this. And so this is always a little bit hard conceptually, but I think it's quite important. And this is a slide I think that is easy to understand for everybody who's doing correlation, some sort of correlation or relaxation spectroscopy experiment. And the idea is the following: we do not view the molecule as a single molecule, as like an individual molecule that is stochastically moving around and folding and unfolding, or binding and unbinding, but we look at the ensemble. So we are starting from a distribution of molecules that is not in equilibrium, and we ask, how does this distribution evolve over time as we just let it relax towards equilibrium, like as we would do if we would do a T-jump experiment. So we take a probability distribution of molecules, we define basically a new equilibrium at a new temperature in this case, and then we let it relax at that temperature, and while it relaxes, we are probing certain spectroscopic observables, and from that we infer something about the kinetics at this thermodynamic state, at this temperature. Okay, and so that's the same idea here, just that this describes really the full probability distribution. So what's the probability of finding the molecule anywhere in state space, not just one observable. Okay, and then we have this operator, this Markov operator, which describes how this distribution evolves. And it's just a purely theoretical and conceptual animal at this point, right? It's nothing that we actually have in our hands. But this has the full information of how this molecule evolves in time. And that means it has all the kinetic information and also all the thermodynamic information. And a key here is that we can, if we're using this language, we can decompose the action of this operator, so how this system evolves in time, in eigenvalues and eigenfunctions of this operator. And basically the eigenvalues are exponentially decaying functions. So, and those are the things that you are probing when you're doing a T-jump experiment or a fluorescence correlation experiment, for example. Basically what you're probing is you're looking at the relaxation of those eigenvalues that have a good overlap, whose eigenfunctions have a good overlap with your experimental observable. So your observable singles out some of these relaxation processes, hopefully the ones you're interested in, like binding or folding, let's say. But basically it's always like this sum of exponential decays. Okay, so in this example, this is 4 well potential. And if we do dynamics on that, of course, we have 4 long-lived states that we are transitioning between with rare events. So in this case, we have 4 eigenvalues that are close to 1. Those correspond to the long relaxation timescales, actually 3 relaxation timescales that are slow, and then 1 eigenvalue that's just because there's a stationary distribution, an equilibrium distribution. So that has an infinite time scale, basically. And then those eigenfunctions here just tell us, okay, the longest time scale is the one where we are transitioning between the left and the right of this barrier. And then the next one is the one where we're transitioning between A and B. And the next one is the one where we're transitioning between C and D, and so on. So these eigenfunctions basically tell us what are the long-lived states in the in the high-dimensional energy landscape. Okay, so if we know the eigenvalues and eigenfunctions, then we can do like the perfect Markov state model, because we can separate the longest lived states, and then we can again use this information to perhaps start new simulations in metastable states that we haven't seen much, or that we just start to explore, etc. And we also can get a very good kinetic model from which we can essentially compute all the long time expectation values and observables that we're interested in, and compare with experimental data, match timescales, try to explain what is the process that this T-champ or this FCS experiment actually sees, and what does that mean in terms of structure, rearrangement, etc. So that's great, but unfortunately we don't have any of this, right, to begin with. We only have some MD engine which generates trajectories. So we have something that starts from a distribution, just individual structures that we start with, and then we run the simulation for some time, and then we find these structures in new positions. Okay, so that's what we have. So essentially we're just randomly sampling this time evolution with our MD. Okay, so now how do we turn this into a learning problem and a machine learning problem from which we can learn this stuff just using the simulation data? Okay, and the key here is this variational approach that we started developing in 2013, and then there were several follow-ups kind of generalizing this idea. And the bottom line is you can approximate these eigenvalues, which correspond to times, physical relaxation times, and these eigenfunctions, which are basically collective variables that describe what your slowest processes are doing. You can approximate them by searching over functions. So you're searching over your collective variables, basically. You're trying to find the slow collective variables describing the slow relaxation processes. And you're maximizing their time autocorrelation. And then there are some constraints, just make sure that the optimization problem makes sense. But that's basically it. So essentially, you're trying to find the slowest collective variables under some constraints. And this is an expectation value that we can evaluate if we just have simulation data. So we just need simulation data. It doesn't need to be in equilibrium, in the sense that it doesn't need to, the starting points don't need to sample from an equilibrium distribution. It just needs to evolve under equilibrium conditions. So no pulling, no laser beam or something like that. So just relaxation under equilibrium conditions. And then we can evaluate this. Okay, and now it's become a machine learning problem, because this is something I can optimize using data from simulations. And so a practical way to do this, to implement this, is such a VAMP net. So a VAMP net is basically a neural network which uses this variational approach to find the best collective variable in this sense. So this the most time correlated or slowest collective variables. And so that basically gives me a space in which I can build kind of the optimal Markov model. And actually in a VAMPnet, it's very easy because I can design it in such a way that the output nodes of this neural network are just indicator functions that tell me with what probability am I in a certain state. And then the VAMPnet is basically doing all the job of taking high dimensional state space variables. So let's say distances or angles that featurize the molecule, or contact maps or something like that, then reduce the dimension in such a way that we find whether the slowest collective variables in that space in a nonlinear way. It's not like PCA or TICA, it's nonlinear. And then also do the clustering in such a way that I can directly extract the Markov state model from the neural network. Okay. And so here's an example. This is alanine dipeptide, where we actually input the Cartesian positions of the atoms. And we don't tell the network anything about that, the fact that torsion angles are important. But it learns to decompose the Ramachandran plot in a very clean way. So it learns basically why that torsion angles are important here to find the slow processes. And this gives us a very clean Markov state model. So this is basically some validation showing that we get a robust estimate of the relaxation timescales after some MSM lag time, and we get a very good prediction of the long timescale behavior from short timescale trajectories. That's what this plot shows. Okay, we can do the same for protein folding. This is NTL9 using the Shaw simulation data and basically find different folded, unfolded, and intermediate states. Okay, so this is an approach to do Markov state model with machine learning. And it can make our lives a lot easier than doing the work that the neural network is doing manually, because if we do it manually, like all the steps of selecting the features, reducing the dimension, clustering, grouping clusters together, estimating the MSM, can all be done. We've worked for many, many years on that and optimizing all the steps, but they're all very error prone, and there are issues with each of them. So it's much cleaner, in my opinion, to have like an end-to-end learning system which does this. Okay, one application I wanted to show of MSMs that we recently worked on, this is on SARS-CoV2 inhibition. So the SARS-CoV2 virus interacts with the ACE2 receptor before being able to enter human airway cells, but it also has to interact with this TMPRSS2 protease, which cleaves part of the spike protein. So one approach is to inhibit this interaction. And there have been two drugs suggested pretty early in the pandemic, Carmostat and Nafamostat. These are drugs that are actually on the market in Japan. And there is indication that they inhibit this this protein, this TMPRSS2 protein. Or actually, first there was indication that it inhibits cell entry of the virus. And there was a hunch that this may be due to TMPRSS2 inhibition. So what we've done is teamed up with a couple of people, Stefan Pöhlmann, who's at a German primate research center. He's doing these cell entry assays, and Mark Rothenberg and Matt Hall at the NIH in their labs. They have set up protease assays for TMPRSS2. And so we've confirmed that indeed these proteins inhibit TMPRSS2 specifically, and set up a Markov state model with MD simulations for this protein. So at that time, there were no X-ray structures for TMPRSS2 available. Now there's an X-ray structure. And we're pleased that it has a state that is contained in our simulations. That's a metastable state in our simulations. But at that time, there was essentially just homology models. So what we did was to start from homology models, run about an aggregate of 0.5 millisecond of MD simulation in an adaptive manner. So building Markov state models on the fly and then restarting in states that we found, but we had little data in. And that gave us a sorry, I don't know something. There's a movie normally here, but apparently that's stuck. So I'm just going to the next slide. So, and that gave us this picture. And this is interesting because it tells us a story about what's the difference between these different drugs. So Carmostat and Nafamostat are both drugs that inhibit TMPRSS2, but Nafamostat does so better than Carmostat with a higher potency. Okay, and interestingly, they are both covalent drugs, and they both have the same covalent state. So they basically both reach the same state, and that's the long-lived state, which is really inhibiting the protein from being able to do its protease function. And it's the same for both drugs, but nafamostat works a lot better than camostat. So why is that? So here you see 3 Markov state models with 3 different drugs. This is camostat, this is nafamostat, and GPPA is a metabolic product of camostat. So that's really the relevant form of camostat in the human body, because the camostat will be quickly processed into GPPA. Still leads to the same covalent state. Okay, so what's the difference between these 3 models is mainly the population of this state here, of this sort of intermediate state. This is sort of a non-covalent state. So this is a state where the drug is non-covalently bound in the binding pocket, and where it's basically ready to undergo a covalent binding. So to where basically the protease will be able to catalyze this molecule and generate this covalent state. Okay, and basically in nafamostat, you have basically a higher probability of being in this state in equilibrium. So in other words, all of these states here, all of these non-covalent states are short-lived in all cases. But in camostat and GPPA, the drug needs to basically try binding and unbinding more often or for a longer mean time before being able to commit to the covalent state than in nafamostat. So you are changing the kinetics of the drug despite the fact that they have the same inhibiting state with the leaving group, because that determines basically how good are your chances to stay bound for a while so that you can undergo the reaction into this long-lived state. Okay, going back to our friend Barnes Barsta. Just telling you how that story ended. So we didn't do 1 million GPU hours for that. We simulated actually for an aggregate of 2 milliseconds, which was quite a lot in 2017. I think now maybe we would do 10 milliseconds or something like that. But it's still something that is still a non-trivial amount of simulation data, let's say, but it's doable with GPU clusters. And this was in simulations that are individually about 1 microsecond long on average. Okay, and then we used Markov state modeling and iterative restarting of simulations in metastable states that we haven't visiting much in order to build up this MSM. And this way we could actually find the bound state from the unbound and find the unbound state from the bound and really discover all these states and connect them so that we would have a fully connected MSM that was able to give us predictions of the binding mechanism and also the binding kinetics and thermodynamics. And we also did some work on, we did perturbation simulations where we essentially computed energy differences upon mutating individual amino acids and asked the questions, how would that change the transition state barrier and the energy difference between bound and unbound states, and correlated that with the plenty experimental data that there is for this protein, and that's correlated quite well. So that's an approach you can use in order to tackle these super long time scale rare events. There are many other methods for sampling rare events. For example, Benoit has many years ago done umbrella sampling on this and also gotten very good agreement of the binding free energy with experiments. But that's kind of a local thing, right? You have to know very well what is the pathway that you're sampling, like bound to just unbound in a similar position, and then you can correct for things like rotational entropy, etc. But if you really have complicated transitions where the protein kind of diffuses around and can do pre-binding at different sites of the other protein, and you don't have like a well-defined reaction coordinate, then there isn't that much. So then you need a lot of simulation data, but you can make the problem turn from an unfeasible problem to a feasible problem with these approaches. Still, it's an expensive solution. In this case, 20,000 GPU days or 500 gigajoule. Or if you translate that into rocket launches, that's about 1/3 of a Saturn V rocket launch to lunar orbit. So you can probably go to lower Earth orbit with 500 gigajoules. Okay. So far so good. I think let me just ask about the timing. So when should I stop?
At 35.
At 35.
Yeah, 15 minutes.
Wonderful. Okay, great. So then I think I'll just skim over the second part. This is and because I really want to talk a bit more about coarse graining MD, because I think that's a very interesting part for you. But just to briefly say this, so we are working quite intensively on other machine learning methods that can help us with the sampling. And that do not necessarily require us to burn rockets every time we want to say something about one particular protein interaction. And so there's this work on Boltzmann generators that we published 2 years ago, but we are continuing to work on improvements and making this actually a more practical approach. So at this time, this was really a proof of concept. But here's just the idea in a nutshell. So as I said, the energy function defines a probability distribution. This is what we would like to be able to sample. But sampling is hard because we get stuck in long-lived states. Okay, and that's a fundamental problem. And in machine learning, there's a big area, an important area that is called generative machine learning, and especially generative deep learning. And the idea is the following: we train a neural network on another function, but often a neural network, which is essentially doing a variable transformation. So instead of just taking some input and outputting some classification or doing some regression with the neural network, this neural network is trying to generate a structure of something that we're interested in, a high-dimensional structure. And it could be an image. So the problem could be learn to sample images of celebrities, given a database of celebrity faces. And that's something that people do a lot in deep learning. So there are all these competitions where you have like this celebrity or other image databases, and you're trying to generate something that looks like it's coming from the distribution, but it's a genuinely new face. But it should be essentially, ideally should be indistinguishable for a human, whether that's a real person or not. Okay. And this is essentially something where we're training a neural network to take a random input distribution, so something that we can easily sample from, such as a multivariate Gaussian distribution, and turn that into one of these faces in this case. And in our case, the problem is defined by the physics. And what we really want to do is we want to sample from the structures from the Boltzmann distribution, ideally just having defined the energy. Okay. And so this is what the Boltzmann generator is trying to do. So it's basically learning a high-dimensional variable transformation. It takes a multivariate Gaussian distribution, pushes it through an invertible neural network, so a special kind of neural network where we can go from Z to X and from X to Z, because then this is a variable transformation where we can use the transformation of random variables rule, and we can write down what is the probability of generating an output. And if we can write down what's the probability of generating an output, we can compare it with the Boltzmann density that we know up to the prefactor, and then we can try to make this similar. To make P of X and E to the minus U of X similar. And okay, so I'll skip over the details for this part, but that's basically the idea. And in a proof of concept, we have shown that this can be used, for example, to sample structures for BPTI. This is an implicit solvent. It's much harder to get this to work with explicit solvent, but that's also something we're working on, and then others are working on that too. But this is really taking a 3,000 dimensional Gaussian distribution, putting it through this neural network, and then you get this structure in one shot. Okay, so it places all the atoms simultaneously in the structure. And this pretty much looks like a protein structure. I guess everybody here would agree to that. And there are a lot of tricks involved in how to make that possible. And there's still a lot of problems too. So I'm not going to lie to you. This is not something you can take off the shelf and throw it on your whatever channel that rearranges in a complicated way. And it's not there yet. But I think it's an important step forward, because it's a method which can, in principle, deal with situations where we have no idea what the reaction coordinates are, and where we are not fundamentally tied to doing tiny steps in state space using some sort of MD method that is wrapped in something else, like replica exchange or umbrella sampling or whatever method. Okay. And it's probably not going to be a standalone method. It's probably going to be something that's complementary with these other methods, but it's something that's conceptually new in this sense. All right. Let me talk about something which is much more practically useful right now, and that's machine learning coarse-graining. And so this is joint work with Cecilia Clementi, Gianni De Fabritis, and our groups. And again, the idea is we have a problem that is a very common problem in physical chemistry or biophysics, coarse-graining. So we want to replace our all-atom force field, or even, let's say, semi-empiric quantum, or whatever level you consider as that is what you would like to really be able to describe. Replace that by something coarser, for example, with fewer particles, that in some sense has the same behavior. Then you have to define what that means, same behavior, in what sense. Of course, you're losing details, so it cannot be the same in all aspects. But a very common definition that is used in coarse-graining is thermodynamic consistency. And basically what that means is, so you define your coarse-graining operation. You define what you keep and what you throw away. So for example, you could just keep the molecule and throw away the solvent, or you could just keep the C alphas, let's say, or C alphas and C betas, or all the heavy atoms, let's say. So you define that, and then thermodynamic consistency means I want an energy function on this coarse representation of my molecule that if I simulate it, so if I throw that into Langevin dynamics or Markov chain Monte Carlo or anything that generates a Boltzmann distribution from this energy function, gives me the same distribution on those variables that I'm keeping than the atomistic simulation would. Yeah, so if you would compute, let's say, all the histograms of all the distances that you still can compute in the coarse-grained representations. So if that would be like a C alpha representation, then you can compute all distances between C alphas, let's say. Then you want the exact same histograms. Then you would get out of an atomistic simulation if you ran it forever. Okay, so that's the goal. So and we can turn that into a machine learning problem by using force matching. And this is something that really Will Noit and Greg both have pioneered. And the idea is the following: we do not only we perform all atom simulations to begin with to train the model, and we are saving not only the coordinates, but we also have to save the instantaneous forces. So that's something we have while we do MD simulations, but they're of course not routinely saved. So that's something that is a little bit annoying if you're not planning to, if you haven't planned to do coarse graining from the time when you started doing the simulations. But I mean, now at least we and several other groups routinely save forces as well. So then, and if we have them, then we can do this. We only need the forces on the particles that we will keep in the coarse-grained representation. So if we want to do a C alpha representation, for example, we only need the forces on the C alphas. Okay. And basically, there's a variational approach, which has been proposed by Will Noit, which basically says, I want to search over force fields now, or potential energy functions that I can turn into a force field by differentiating them with respect to the atom positions, such that I am matching my forces, my instantaneous forces, after the coarse graining operation has been applied, on average. So basically what that says is, I'm trying to learn the mean force. The mean force is what you get for every position of your coarse grained beads if you average over all of the fine-grained stuff that you're throwing away, all of the solvent and all of the atoms that you're not keeping, you Boltzmann average over that, then you have the mean force on your coarse-grained atoms, and that's what you're trying to match. But we do not need to compute the mean force explicitly. That would be actually very hard. We can use the instantaneous forces and just throw it into this ensemble average, and that's doable. Okay, and then we have shown in our paper that we can actually view this as a machine learning problem. We can decompose this error into different parts that are systematic error and that are noise. Noise is something that we cannot do anything about. It's just something that we can fight with more data. But there's bias and variance. That's something we can play with by choosing our model. And the bottom line here is that we are basically learning a neural network energy function, which is this coarse-grained energy. And we are computing the forces from this energy function sort of on the fly by using backpropagation, so automatic differentiation. And that's what we're then comparing with the instantaneous forces. And that's what we're trying to match. And the prior energy here is a very important part. So if the prior energy basically contains things that avoid our energy function from predicting things that are nonsense in states that it hasn't seen. For example, if it could predict that if two atoms were overlapping, the energy would be low because it has never seen the state in the simulations. So we need to somehow add something to enforce the right asymptotics, the right physics, basically. Okay. This shows that you, with alanine dipeptide and throwing away all the solvent and all the atoms except for these 5 here, we can essentially learn a perfect Ramachandran, almost perfect Ramachandran plot. That's this. Yes, that still has some errors. But there are better models now, which is something we cannot do with the spline model. So let me say what a spline model is. Spline model is what is the sort of standard force field you would construct on your coarse-grained atoms. Now you take your coarse-grained atoms, you compute distances, angles, torsions, and you learn some functions of those. And then there are some problems that you cannot fix with that. And that's a fundamental issue with coarse-grained models and these kind of energy functions that we're writing down in the coarse-grained models. When you coarse-grain, when you throw away all of this fine-grained information, then the energy function on your coarse-grained variables is becoming more complicated. It's becoming a more multi-body function, because you have to kind of infer information about all of the degrees of freedom that you threw away from the ones you keep. So it becomes more multi-body, right? So and that's becoming very, very hard to come up with a functional form as a human that you can parameterize that describes the coarse-grained model well. That's kind of the main problem with coarse-grained force fields. But we do not need to worry about what exactly is this functional form. It could be something very complicated, but we can learn these functions with neural networks as long as we have the right optimization principle. Okay. Okay. Same with Chignoline, where the spline model basically doesn't even predict that there's a barrier between folded and unfolded, and the CGNet gets it qualitatively right. And to wrap up, I just want to say, so now what we're doing is that we're using specific neural network structures for the neural network, and one that we like a lot is called SCHNET. That's named after the first author here, Christoph Schütt and Klaus Robert Müller's group. And that's basically a neural network that is very much built like you would build an energy function. So it basically looks at individual atoms, and then it kind of incorporates information about the other atoms that this atom is interacting with, and does what's called a continuous convolution, and is doing that in multiple layers. And with that, you can learn multi-body information if you stack this multiple layers deep. And so with these approaches, we're getting much better CGNets, so much better machine learned coarse-grained energy functions than with the ones that do not have a particular structure. Here's just a folding trajectory of Chignoline using such a CG SCHNET. Sorry, the names are getting more and more messy. And the latest thing that we've been working on is using this to learn an implicit solvation model. Okay, implicit solvation is basically coarse-graining in this, or can be phrased as coarse-graining in this sense. So we just throw away all the water, and we want to learn an energy function for the molecule that is giving us the same mean force. So the potential of mean force should be the same. So that means we are learning the solvation-free energy using coarse-graining, so using forces. Okay, and we can use that using we can do this using the exact same framework. And now the prior energy, so our baseline energy that we input into the model, that the model doesn't need to learn, is actually the vacuum energy of the molecule. So the intramolecular energy, because that has all the relevant physics of the molecule itself. And then the only thing the model really needs to learn is the solvation-free energy. And well, with this, we can essentially learn an exact implicit solvation model. So that means an implicit solvation model that exactly, of course, how exact depends on how much data we can throw at it to beat the noise, to beat the signal to noise to get the signal to noise ratio up. But in this limit that we can generate enough training data, we can learn a function which gives us the same, basically the correct implicit solvation term representing the explicit solvent model that we use as a baseline to train. Okay, and here we see again in alanine dipeptide that obviously we're doing better than the vacuum case, but we're also doing, in this case, slightly better than the GPSA model, and in Chignoline a lot better than the GPSA model. And
I just say that your time is over, and you have so many questions if you want to have them all.
And I'm done. So that's perfect. Good. So let me just wrap up. So why do we do deep learning? So one thing that's important for me to communicate is machine learning is not just kind of matching inputs to outputs. So, I mean, probably the vast majority of machine learning is supervised learning, where we have some image or some protein structure or whatever, and we have something we want to match to, like molecular energy, for example. And okay, then we have generating this training data somehow. But if we're building on solid physics, then we have a lot more, and we can get our learning principles from the physics. We don't have to rely on somebody labeling some data. We can really do fundamental science using machine learning as a tool that helps us to make our life easier, basically. And deep learning is nothing else than an approach to program any computation and fit the parameters in that computation in an automatic way. And that's, I mean, we're all using computers. Many of us are computational scientists and run MD simulations or fit models, etc. So deep learning is just an automatic way to do all that and find the parameters in an automatic way, right? So it's no different than all of the model building that we are doing manually. It's just kind of doing that in a more automatic and potentially more powerful way. And that's really what deep learning is. It's an automatic way to express arbitrary computational graphs and parameterize them. And in that sense, it's just essentially think of it as the next level of linear algebra, right? You cannot do just any computation in the computer. You can do any computation and learn the parameters if you have some principle to do that. And that's how I'd like to think about it. And with that, I'm really done. Thanks a lot to my group and our collaborators and funders, and thank you for your attention.